So once we can't do the factoring to graph polynomials, we look at synthetic division to help me find those zeros. So again, this helps you find your zeros. You're essentially just saying the y values are zeros, and then you find a number for your x, which I keep repeating is an x-intercept. But we're going to use synthetic division now, because here's an example. This polynomial, there's no GCF. There is 4 terms, so we can try to factor by grouping. But the purpose of factor by grouping, even though here the GCF would be x squared, leaving us with 2x minus 7, and the GCF of the next two is a positive 4, leaving us with x plus 1. These two binomials do not match. And that's the purpose of factoring by grouping, is that you split the first 2 terms and the second 2 terms, and you find the GCF of the first 2, GCF of the second 2. And you're left with a binomial on each term, on each, the first and the second. You're left with a binomial that are identical. But that's the only method we have for 4 terms. That's why we revert to using synthetic division to help us find these zeros. And because they're zeros, they are also factors. It's like working backwards, because the method we were using, we were factoring to find our zeros. But this method, using the synthetic division, is backwards. You can find your zeros, and then if you want the factored form of a polynomial, you can get it. We needed the factored form to be able to get our zeros. This synthetic division finds a zero first, and then you can find your factor. But we'll do that later on in the video. But if you don't remember synthetic division, it uses this sort of upside down symbol, this sideways L. And the benefit of it is very efficient and only uses the coefficients. So here we would only use all the coefficients. And the only downside is when it comes to dividing, because synthetic division, you can only divide by a linear factor. You can't divide by a quadratic, a cubic, only linear. And some nuances about synthetic division is, remember, a polynomial is written in descending order, so 3, 2, 1, 0. If any of these powers are missing, we will use 0 as a placeholder for any of those missing terms, because you're going to notice synthetic division has this pattern, and if you're missing a term, it's going to throw the pattern of the synthetic division off. And then once you're done applying your synthetic division, you're going to be left with a quotient. And that quotient is actually a new polynomial with a degree n minus 1, just meaning that it has gone from, like, for example, power of 3 to power of 2. And that's going to be useful, because as we decrease that power, it's going to help us lower the number of zeros that we have. And a cubic can be tricky to find if it's 4 terms or if it's just 2 terms. But once you say, for example, here, if we were able to decrease this from a power of 3 to the power of 2, we know any quadratic can be solved using the quadratic formula. So that's going to help us, that we don't have to go all the way 3, 2, 1, decreasing this polynomial. We just need to get down to a quadratic so that we can use our quadratic formula. But let's see an example of how this synthetic division works. So here we have, if you notice, power of 3, power of 2, and then the constant, we're missing that 1. So when you do your synthetic division, so I'll set it up here, it's going to be 3 for that first one, 1 for the second one. But this is where I meant where you need to put a 0 as a placeholder. And then lastly are 3. Now you would think, okay, since we're dividing, we're going to use this coefficient, that one coefficient, and that's not how it works though. It only uses, and I should probably include this here, it only uses the constant term to be able to factor. Now, if you notice, it does say x minus c, but here we have x plus 1. So if we make a quick note, we're actually, if we rewrite it in this x minus c form, this would say x minus negative 1. So the number we're actually using is negative 1 to divide by. So just something to note. If it was x minus 1, then it would be a positive 1 here. The negative comes from the property of synthetic division. But, of course, two negatives multiply and make a positive, and that's why you don't see the minus here. But you have to represent it as a negative 1. Now, this is how we work through our synthetic division. So, first one always comes straight down. There's nothing you do about that. This one. It just comes straight down. It's a 3. But then, similar to long division, once you have a number, right? If you remember when you wrote a number up top, you always multiplied that back to your divisor. So 3 times negative 1 is going to be negative 3. So you multiply these two together, and the product goes in the next column. And then you add going down, so that's going to leave us with a negative 2. And then once again, you multiply again. So that's going to be negative 1 times negative 2. That product is going to go in the next column, which is going to be a positive 2. We add vertically. It's going to leave us with a positive 2. And then again, you multiply back. That's going to leave us with a negative 2. And then you add vertically. This is going to leave us with a positive 1. And this is our remainder. This very last number is your remainder. But like I said, this is a new quotient. So if we had a degree 3, and then that leaves us with a new polynomial with degree n minus 1. So that's going to be 3x squared minus 2x plus 2. And if you notice, I'm using the coefficients from here plus our remainder, which is just the 1. And it's still being divided by that x plus 1 since it didn't go all the way through. Now, if this last one became a 0, I would have no remainder. But if I had no remainder, that would tell me that this is a 0 of this polynomial. This negative 1 would be a 0. And let's see that in this next example. That gets illustrated. So we go here. So we have 2, 7, and then 6. Which we can factor this because it's a quadratic, or we can use a quadratic formula to break it down. But once again, let's make a quick note. We have this x plus 2. It's really x minus negative 2. And that's what I'm going to use when I do this. So remember the first one, it comes straight down. You multiply. You multiply here, and the product goes in the next column, which would be negative 4. You add vertically, and that gives you positive 3. Once again, you multiply back to the divisor. That gives us negative 6, and that is our bingo. That's what I'm looking for. I'm looking for a 0. Now, we're going to talk about different definitions, but this being a 0 tells me that this is a factor of this polynomial. Here's the 0, this one's the factor, right? If this was a factor, we would take that factor, set it equal to 0, and we would solve to get -2. That's where the -2 part is the 0, and the x plus 2 is our factor. So remember what I said, synthetic division works backwards. You find your 0, and then you can find your factor. But remember, it also, this was a quadratic, it got decreased by 1 power. So that becomes 2, instead of x squared, is just x plus 3. And this is also my factor that I can attach it with x plus 2. And that is exactly the factored form of this quadratic. Right? Because if we were to use the x or diamond method, remember you multiply the constant coefficient with, the leading coefficient with the constant coefficient. That gives me 12. And then I put 7 in the middle. What numbers work to do this? We can do 3 and 4. And remember, like I said, you write those. Once you're done finding those two numbers, you write your factor. But because the leading coefficient is 2, whatever leading coefficient is, I divide them. But like I said here, 4 is divisible by 2, so that will become x plus 2. But because 3 is not divisible by 2, I just write it up front. And that's exactly the same factor. And this is how you can see how synthetic division is going to help us do those zeros, / help us do the factoring for problems like this that aren't able to be able to factor. But I needed this part, right? For here, I was given this x plus 2. Looking at this first example, I don't have that x plus 2. So how do I find that? Well, that leads us to this theorem that we have. That's known as the rational zeros theorem. That if a polynomial p of x has an integer, not integer, coefficients, and p over q is rational, is a rational 0 of p of x, then p over q is equal to all the factors of the constant coefficient. So remember, that means the very last term on a polynomial, divided by all the factors of the leading coefficient, which is the first part of the first term. It's the coefficient of the first term of a polynomial. Now, what does this do? This is going to help me find these possible zeros. So that's a good note. This little theorem and formula only helps me find possible rational zeros. Does not find anything irrational or complex. So that's with i's that I slightly talked about before. So this idea allows us to find a list of possible zeros. And we're going to use synthetic division to help us do this. So here we go. We have our P. Remember, P is the constant. Q is the leading. And all I have to do is divide the different combinations of factors. So we start with P to make my list. So the factors of 4 are plus or minus 1, plus or minus 2, and plus or minus 4, right? Those are all the numbers that make up 4. And then I have my Q, which is plus or minus 1 and plus or minus 2. And now I have to just divide every combination. So the way I like to do it is I just take every factor in the numerator and divide it by the first factor in the denominator. Then I take every factor in the numerator and divide it by the second factor in the denominator, and so on and so forth, to make my entire list. So this is what it will look like. Plus or minus 1 divided by plus or minus 1, plus or minus 2 divided by plus or minus 1, plus or minus 4 divided by plus or minus 1, which clearly that's going to make let me move this down to be more efficient. That's just going to make a list of plus or minus 1, because 1 divided by 1 is 1. 2 divided by 1 is 2. And just write the plus or minus, because you get to test each one. And then 4 divided by 1 is going to be 4. And then you take each one of these again and divide it by your 2. 1 divided by 2 is a half, so it's going to introduce another possible 0. But 2 divided by 2 is 1. It's already a possible 0. We don't have to do it again. And 4 divided by 2 is another possible 0 that we don't have to try again. Now the issue is, if you notice, this has 2, 4, 6, 8 different possible zeros. But let's not forget the fundamental theorem of algebra. The degree tells us the number of zeros that we should have. So this should only have 3. Hence, all of these are not going to work. That's where this can get a little tedious. There's no quick way of thinking about it. You just need to test them. Sometimes it's going to be the fractions. I know sometimes we don't like fractions, but sometimes that's what's going to work. Luckily, I know which ones work. So for the sake of time, I will use them. So 2. And once again, look at the coefficients. And then we'll look at the powers. 3, 2, 1, 0. So none are missing. I'm not going to need a 0 as a placeholder. This is going to be 2, -7, 4, and 4. Don't forget, the first one always comes straight down. You multiply back to your divisor. That's 4. You add vertically is -3. 2 times -3 is -6. You add vertically is -2. You multiply across. 2 times -2 is -4. And look, bingo. That's exactly what I'm looking for. So that tells me that this is one of my zeros of my polynomial. Next is, because I did that, I have this new polynomial, right? And there's no remainder to worry about. And let's not forget, the polynomial has now gone from cube to this is a square, meaning that we have a quadratic. So that means, sure, can I keep doing the synthetic division to try to find this the rest of my zeros? You can, but once you get to a quadratic, you want to be efficient with your time and just factor this like you normally would, which would be a 2 times -2, which would be -4, and then -3 will be here, and then it'll be -4 times 1, which we write our factors x minus 4, x plus 1, and then that leading coefficient is a 2. I divide that to each, and that leaves me with x minus 2 times x plus 1/2. So I would be able to factor this. Oh, sorry. You can do that, but it probably is nicer if you just write x minus 2 and 2x plus 1. Which, that 2x plus 1, when you try to find your 0 by setting it equal to 0, is going to give you -1/2. And then this 2 is going to give you a +2. And for the sake of practicing these, I will do another synthetic division using these new zeros. I don't need that last remainder. But if you notice, we saw that -1/2 would work because we factored this quadratic. Let me make a quick note. here, that is 2x squared minus 3x minus 2, which you can factor using whatever methods work for you. So the first one always comes down. 2 times negative 1/2 is negative 1. We add vertically. Negative 1 plus negative 3 is negative 4. Times a negative half is positive 2. You add them, and look, we get our 0. And that very last one, it went from power of 3 to power of 2. This is a power of 1. So this one, which I'm going to move over here, is like saying 2x minus 4, which I can just set equal to 0. And when I add the 4 to the right-hand side and then add the 2, divide the 2, I'm going to be left with another 0 of 2. And then here are my 1 0. So here's 1 0, 2 zeros, and then another one. So something you should notice. Just because 2 worked once doesn't mean it can't work again. Let's not forget, polynomials have multiplicity on their zeros, meaning that they can repeat. So this would be my 1, 2, 3 different zeros. But let's move on to the next example to just practice doing these zeros, and then we'll come back to seeing like what we would do to either factor them or to graph them. So once again, our P over Q. So our P in this example, don't get mixed up this P of the function notation with P of the constant coefficient. Not the same thing. So luckily right now the constant coefficient, all you have is plus or minus 1. I know it's a negative one, but you're just thinking about the factors of 1, which is just 1. So there's no other factors there. And for Q, our factors are plus or minus 1 and plus or minus 2. This is going to make a nice short list. Remember, I take every term in the numerator, factor in the numerator, divided by each factor in the denominator. So 1 divided by 1 is 1, and then 1 divided by 2 is 1/2. So here, I'm going to make my synthetic division. So 4, 3, 2, 1, 0. There's no missing terms. So I'm just going to use the coefficients. 2, 7, negative 3, negative 5, negative 1. And like I said, for the sake of time, I know the zeros. So I'm going to start with 1. You might not always be able to finish right on the first one you guess. It might take multiple tries. 1 times 2 is 2. Plus 7 is 9. Times 1 is 9. Plus negative 3 is 6. Times 1 is 6. Plus negative 5 is 1. Times 1 is 1. And we get our 0. Perfect. And just because 0 worked doesn't mean it can't work again. But we went from a power of 4 to a power of 3. Remember, I like to stop at a quadratic. So let's keep going with this new polynomial. I like to keep going, building off the iteration, so I can keep making it smaller. Because if I try to restart using some of these zeros on this old one, again, I'm still using the entire polynomial. If I keep building off of these iterations, it can help make it smaller. Now, let me show you what happens when something doesn't work, right? We try this. So that we bring down the 2 times negative 1 is negative 2. We add a 7. We multiply to the negative 1. It's going to give us negative 7. We add is negative 1. We multiply negative 1 times negative 1 is 1. But 1 plus 1 is 2. And again, that is my, how do you say it? That is a remainder The reason why I'm xing it is just that this is not a 0 of my polynomial. But the luckily, or the benefit of this is that now I know for sure if -1 didn't work once, it's never going to work again. So this starts decreasing the number of iterations you're going to do. So let's try that same one, 2961, and then I'm going to multiply, or I'm going to choose a factor of -1/2 to test. Let's not forget, our first one always comes straight down. 2 times -1/2 is going to be -1. You add, that's 8. You multiply times the -1/2, it's -4. You add, it's 2. 2 times -1 is negative. 2 times -1/2 is -1. We add, and bingo, here is our next 0. But like I said, this is now a new polynomial that has decreased by 1 power. So we went from power of 4 to power of 3 to now we're at power of 2. So that is a quadratic. So I'm going to bring this up. Now quadratic is 2x squared plus 8x plus 2. And again, I'm trying to find my zeros. So I set it equal to 0. But there's a slight problem here. Right? I take the leading coefficient, the constant coefficient, and I multiply them. That gives me 4. Then I take my middle term, that gives me 8. But the only way to multiply to 4 is 4 and 1, 2 and 2, and that's it. There's no other combination to multiply to 4, which means 4 and 1 doesn't add up to 8. 2 and 2 doesn't add up to 8 either. So if this can't be factored, do I keep doing the synthetic division? No. We use our quadratic. We use our quadratic formula. Hopefully, remember this is for a quadratic, ax squared plus bx plus c. And what's a quadratic formula? If you remember, it's x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. And we can see our a is this 2, our b is this 8, and then our c is this 2. So we can plug that in. So don't forget, this negative here is coming from the formula. And b is an 8 plus or minus the square root, and then b again is 8 squared minus 4 times a is 2. And then c is also 2. All over 2a is 2. Then we slowly simplify. So it's -8 plus or minus the square root of 64. 4 times 2 is 8, times 2 is 16, minus 16, all over 2 times 2 is 4, which is equal to -8 plus or minus the square root of 48 over 4. Now remember, we did review how to simplify these. If you don't know what multiplies to, what two factors multiply to 48, you can break this down to 4 and 12, 2 and 2, 3 and 4, and then 2 and 2. Remember, this is looking for groups of 2, not necessarily the number 2, but just groups, pairs. And here is a pair of 2's. Here's another pair of 2's, but let's not forget about this 3 that's still here. This 3 that's still here. But these two, remember, for each group, you're allowed to simplify one of them. So one of the 2's comes out from this group, and another 2 comes out from this group. And since they were multiplying inside, those are going to multiply outside, which will leave us with -8 plus or minus 4 times the square root of, and don't forget the 3 that's still inside, over 4. Now, if you notice the numerator, they have a GCF of 4, which will leave us with -2 plus or minus the square root of 3 all over 4. And we're doing this because we notice that you can simplify them. And that's going to give us -2 plus or minus the square root of 3. And if you notice, those are our zeros. We have 1 0, 2 zeros, and this is 3 and 4 because there's a positive one and there's a negative one. And when we look our degree is 4. So we need 1, 2, 3, 4 zeros. But like I said, this only helps you find rational zeros. This is an irrational number, so you would have tested these out and you would have never found these other 2 zeros. That's why it's important to stop at a quadratic, so that if this situation happens, you can take a different route, either factor or use a quadratic formula. Now let's do one more that involves finding our zeros. So once again, this is going to be our Q. Here's our P. So the zeros for P are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Our Q luckily only has plus or minus 1, plus or minus 2. Remember, we have to divide all of these. Now, for the sake of time, I'm just going to say 1 divided by 1 is going to give us 1. 2 divided by 1 is 2. 3 divided by 1 is 3. 6 divided by 1 is 6. And then we continue. Now, we do all of them divided by 2. 1 divided by 2 is going to be plus or minus a half. And then we do 2 divided by 2 is 1, which we have. 3 divided by 2 gives us 3 halves. And 6 divided by 2 is 3, which, right, 6 divided by 2 is 3, and which we already have 3. So this is our entire list, which I'm going to move over so I can just fit this last possible zero. Remember, these are just possible zeros. And then we can use our synthetic division. Make sure you have 3, 2, 1, 0, all in descending order, no missing terms. So we can jump right into finding our zeros. Once again, luckily I know which ones work. So I'm going to start off with a half. At any point you can stop the video and try to work through these. So 2, you multiply times a half, that gives you 1. You add, that gives you 2. You multiply, gives you 1. You add, it gives you -12. You multiply, gives you -6. And bingo, exactly what we were looking for, that 0. But now we went from power of 3 to this is a new polynomial of a power of 2, which is going to be 2x squared plus 2x minus 12. Again, if you want to keep going, I wouldn't recommend it. I would just go straight to, okay, here, remember, don't forget, it's 2 times -12 is -24. And then the 2 goes here at the bottom. The two numbers that satisfy this are going to be 6 and -4. That means I'm going to go right into my factors of x plus 6 times x minus 4. And remember, I take the leading coefficient and I divide those constants, which both of them are divisible by 2. That leaves us with factors of x plus 3, x minus 2, which remember the goal is I'm trying to find zeros. So if I set this equal to 0, the x plus 3 is going to give me a 0 of negative 3. The x plus 2 is going to give me a 0 of positive 2. Right? Because if I set this equal to 0, I subtract the 3 over, I get negative 3. I set this x minus 2 equal to 0. It's going to then give me 2, which, remember, a fundamental theorem of algebra says we need 3 zeros. We got 1, we got 2, and we got 3. And they all have a multiplicity of 1. Sometimes they repeat, sometimes they don't. But I'll stop the video here, and this is just using synthetic division to find your zeros. But don't forget, once you have your zeros, all you need to do is plot your zeros, do your end behavior, and you can graph them. Actually, I'm going to just copy this graph because it is that quick. I'll just graph them really fast. So the zeros in this example was 2 and a negative 1/2. And remember, this 2, positive 2, had a multiplicity of 2 because there's 2 of them. The degree is 3. The leading coefficient is 2. So I know it goes up on the right, down on the left. But at negative 1/2, the multiplicity is 1. So I know I need to go through. But then at 2, the multiplicity is 2. So I know I only touch it and then go back up, which falls in line with my end behavior. Next example, same thing. We have our zeros. So we have a 0 at 1. Then we have a 0 again at a negative 1/2. So it's right here. And now these are two separate zeros. Right? So it's negative 2 plus square root of 3. And then it's negative 2 minus square root of 3. Now using a calculator, this is approximately 0.3. Sorry, negative 0.3. And then this next one is negative 3.7, which makes these points here. I'm actually going to erase it. I'm going to make this a little bit wider. Just because we need the room. So this represents 1. This represents 1, 1. This is 2. This is negative 1. This is negative 2. So the scale's a little off just so we can make it fit. But we had a 0 at 2. Sorry, at 1. And then we have a 0 at negative 1/2, which is 0.5. But then we have this other 0 at negative 0.3, which is right about here. So again, that's this one's that one right there. And then negative 3.7 will most likely be, or sorry, not most likely, it would be over here. So this is negative 3. And then 3.7 is closer to negative 4. But the degree is even with the leading coefficient that's positive. So I know on the ends, it's going to go up on the right, up on the left. And each one of these had a multiplicity of 1. So it's odd. So I know I need to go through here, through this next one, curve back down through here, and then through that one. When I say through, it's because we're going from one side of the x-axis to the other. We went through, and through. And then here, it's just such a tight gap. Again, if you want to know exactly what's going on, you can use like negative 0.4, and you can see exactly how high. You can use 0 here to see how low it goes, which if you look really quick, if I plugged in 0, 0, 0, 0, 0, all these would cancel. My y value would be negative 1, which it would be right here. So without trying, I actually graphed roughly where it should be. And let's do this last one really quick. So our zeros are a half, positive 1/2, which is here. We have a 0 at positive 2. We have a 0 at negative 3. The degree is odd. The leading coefficient is positive, so I know it goes up on the right. Up on the right, down on the left, which means, and they all have an odd multiplicity, so it's going to go through here, through the next one, and through the last one, which matches up with the end behavior. And that's it. Once you can get your zeros, the graphs happen really quickly, right? And I just want a rough sketch. I don't need it to be perfect. I also don't want it to be just some random graph, but that's the breakdown of using synthetic division. And then this definition here says P of C is 0 if and only if x minus c is a factor. So like I said, with synthetic division, we find our zeros, then we can find our factors, which, again, the factors are in the form of x minus c. So because this has 3 zeros, that is also the same thing as saying it must have 3 factors, which all you have to do is input these factors. So this is going to be x minus 2, x minus negative 1/2, and then another x minus 2. And this is the factored form of that polynomial. Don't forget, these two negatives become positive. With this next one, same thing. If I wanted a factor, there needs to be 4 of these x minus c's. That's exactly what this definition says. If c is a 0, then x minus c is your factor. So if this is a 0, this is a factor. All we have to do is plug them in. So it's x minus 1, x minus negative 1/2. And then these are tricky because it's x minus and then negative 2 plus square root of 3. And then x minus negative 2 minus square root of 3. And there's my factored form. And last but not least, this has degree 3, so it needs to have 3 factors. So that's just going to be x minus 1/2, x minus negative 3, then x minus 2, which we can simplify to x minus 1/2, x plus 3, and x minus 2. And here is my factored form of this polynomial. So that's what ties this all together. Instead of doing your factors, then find your zeros, synthetic division, find your zeros, and then you get your factors. And you can, once you have your zeros, I mean, the graphs are pretty quick after that.